In this lecture, I will discuss solution to some specific problems from chapter number 4 of the textbook of Mechanics of Materials by Baer and Johnson, 7th edition. The chapter is about pure bending. The first problem from the exercise of the chapter which I have chosen for this lecture is problem number 439. A copper strip with the modulus of elasticity EC equal to 105 gigapascal and an aluminum strip EA equal to 75 gigapascal. This is modulus of elasticity. They are bonded together to form the composite beam shown in this diagram. Knowing that the beam is bent about a horizontal axis by a couple of moment 35 Newton meter, remember that moment is around the horizontal axis. So we have to find I about the horizontal axis, and we have to find centroid of the cross section, horizontal centroid. Determine the maximum stress in the aluminum strip and in the copper strip. We know that maximum stress always occurs at the outermost surfaces of the cross section. So for aluminium, maximum stress will occur at the outermost surface here, at this surface, and for copper it will be at the outermost surface of copper. Okay. First, we have to discuss about the centroid. Because moment is about a horizontal axis, centroid will be horizontal, and around horizontal axis, this beam is not symmetric. Material above the horizontal axis is aluminum, and below it is copper. So the centroid is not simply the midpoint between the top and the bottom layers. We have to find the geometric center. Before that, we have to convert this beam into, or transform this beam into a single material beam, because it is a composite beam. So we have been given two values of modulus of elasticity. I will find n, which usually I do by dividing the greater value of modulus of elasticity over the smaller value. In this case, EC is greater than EA, so I am dividing EC by EA. You can do it like the smaller value divided by the greater value. The only difference will be that n will be greater than 1 or smaller than 1. If n is greater than 1, the area of this transformed section will increase. And if n is less than 1, area of the transformed section will decrease. Because we have to multiply n with the width of the transformed section, or width of the material which we want to replace with the other material. In this case, I have divided EC over EA. So copper modulus of elasticity for copper by modulus of elasticity for aluminum. So I want to replace copper with aluminum, and this whole beam will be totally made of aluminum. Okay. Problem number 439. N is equal to E for copper divided by E for aluminum. E for copper was given to us, it was 105 gigapascal, and E for aluminum was 75. So total value becomes 1.4. N is greater than 1. Okay. Initially, the aluminum section was 24 mm wide and 6 mm deep. Copper at the bottom has been replaced with aluminum. The width will increase because n is greater than 1. How much has it increased? It is 24. Initial width was 24. So 24 multiplied by n. So the total width of copper section, which is now made of aluminum, is 33.6 mm. This whole cross section is made of aluminum. This is transformed cross section. The area 1 was already made of aluminum. Area 2 is a transformed section made of, now it is made of aluminum. So this whole cross section is made of a single material. We can find its centroid now. Okay, to find centroid, first we need to find areas of section 1 and section 2, then their individual centroids, and then we can find total centroid. Okay, individual centroid of area 2 and area 1 from a reference line. For example, this bottom surface is our reference. So this is Y2, mid of section 2, and this is Y1. Y2 is the height of the beam is actually the same, cross section it is same. Okay, so Y2 will be half of 6, it will be 3 mm, and Y1 is 6 plus half of the top 6. This 6 is total plus half of the top portion, so it is 9 mm. Okay, so we have to find total Y dash, total centroid from the bottom. I will make a table here. Section 1 and section 2. Area of section 1 in millimeter squares is 24 into 6, which becomes 144 millimeter squares, and area of section 2 is 33.6 into 6, which becomes 201.6. Okay, Y dash in millimeters from the bottom surface. For section 1 it is 9 mm, and for section 2 it is 3 mm. The product of A and Y, product of the first column and the second column. So 144 multiplied by 9, it becomes 1296 millimeter cube, and product of 201.6 and 3 becomes 604.8. Now we can add the two areas to find summation of area by adding 144 and 201.6. So the sum of the areas becomes 345.6 millimeter square, and sum of the product of A and Y dash becomes 1900.8 millimeter cube. Now to find total cross section, total centroid of the total cross section, we have to use this expression which the students must know from their engineering physics. Summation of the product of A and Y dash divided by summation of area. So it will be 1900.8 divided by 345.6. So it becomes 5.5 millimeter. So centroid of the transformed cross section is 5.5 millimeter above the bottom line. 5.5 millimeters. It is almost here. Y dash is 5.5 millimeters from the bottom surface. Okay, so here is our centroid line. Now we have to find I, the moment of inertia for the cross section. So I is equal to I dash plus AD square. I dash for rectangle is BH cube by 12. We have two rectangles, rectangle 1 and rectangle 2. Both the rectangles have different widths Rectangle 1 has a width of 24 mm and rectangle 2 has a width of 33.6 mm. Height for rectangle 1 and rectangle 2 both are 6 mm each. Area of rectangle 1 and rectangle 2 both are known. It is 144 mm square and 201.6 mm square respectively. And D1 and D2, D is actually, this D is actually the distance of the centroid of each section or each area from the centroid of the total cross section. Centroid of the total cross section is here, Y dash, and centroid of the area 1 is here. This distance is D1, which is actually it must be 3.5 because this total height from bottom is 9 mm. 9 mm minus 5.5 becomes 3.5 millimeters. D1 is 3.5 millimeters. D2 is centroid of the cross section 2, centroid of the area 2 from the total cross section centroid. So total height is 5.5 mm. Sorry. It is this point. D2 will be 5.5 minus 3 mm. So 5.5 minus 3 mm becomes 2.5. D2 is equal to 2.5 mm. So D1 and D2 are also known to us. A1 and A2 are known. B1, B2, H1 and H2, everything is known. So it will be B1 H1 cube over 12 plus A1 D1 square plus B2 H2 cube over 12 plus A2 D2 square. Okay. B1 is equal to 24 mm, B2 is equal to 33.6. So 24, height is 6 divided by 12 plus A1 is 144, D1 is 3.5 square plus B2 is 33.6 mm. H2 is also 6 divided by 12 plus A2 is here 201.6 into D2 is 2.5. Okay, so I becomes, total I becomes, in millimeters it will be 4060.8 millimeter power 4. If we want to convert millimeters into meters, 1 millimeter is equal to 10 power minus 3 meters. So it is 4060.8 into 10 power minus 12 meter power 4. Or we can rewrite it as 4.0608 into 10 power minus 9 meter power 4. Now in order to find maximum stress in aluminum and copper, we have to find distance of the aluminum area from the neutral axis, distance of the outer surface of the aluminum, and distance of the outer surface of copper from the neutral surface. Now we will come back to this diagram. Area 1 or section 1 is actually aluminum. In the given, again I will show it to you. The top area is aluminum, the bottom one is copper. So we have already established the neutral axis is somewhere here, 5.5 mm from the bottom. So we have to find distance of the outer surface of copper and distance of the outer surface of aluminum from the neutral axis. So we can do it in this diagram. From the neutral axis, This is neutral axis. From the neutral axis till the top of the aluminum, CA, total height is 12 mm. 6 plus 6. Out of 12, we have subtracted 5.5. So C1 becomes 6.5 mm or 0.0065 meters. And C2 is distance from neutral axis to the outer surface of copper. So it is similar to Y dash. C2 is, or CB is, sorry, copper, C copper is 5.5 mm or 0.0055 meters. Okay. First we will find maximum stress in aluminum. In aluminum, the maximum stress will occur at its outer surface, mc of aluminum divided by I. C is distance on neutral axis from the outer surface of aluminum. Moment is given 35 Newton meter. Ca is 0.0065. I is 4.0608 into 10 power minus 9. So sigma maximum in aluminum comes out to be 56 into 10 power 6 pascals or 56 megapascals. Similarly, sigma maximum in copper is equal to moment into C of copper divided by I. Moment is 35 Newton meter. C for copper is 0.0055 meter divided by I is 4.0608 into 10 to the power minus 9. So it comes out to be 66.4 into 10 power 6 pascals or 66.4 megapascals. So we have just calculated maximum stresses in both copper and aluminum. For maximum stress, we know the expression is mc over I. Moment is same for the whole cross section. I is same for the whole cross section. We just need to know C for aluminum and C for copper. C is distance of the outer surface from the neutral axis. We have found neutral axis by finding the centroid. Centroid has been found using this expression, summation of A y dash divided by summation of A. We have divided the cross section into two different areas, area 1 and area 2. Area 1 is area of aluminum, area 2 is transformed area, which was initially copper, but we have transformed into aluminum by using N, which is ratio of 2 moduli of elasticity. So rest I is actually sum of the I for aluminum section and I for the copper section, I1 and I2. So I hope it is very easy to understand. We will move towards our next problem. The next problem which I have chosen for this lecture is problem 4.55. This problem is of the same nature as the previous one, but it is a little bit easier because it is symmetric about the horizontal axis. There is steel at the mid and there are brass and aluminum above and below the steel. The dimensions of the bars of aluminum brass above the steel and below the steel, they both are similar. So it is symmetric. We do not need to find centroid around the horizontal axis, in the horizontal direction actually. We will simply take the midpoint between the top and the bottom surfaces. The statement is 5 metal strips, each 0.5 into 1.5 inch cross section, are bonded together to form the composite beam shown. The modulus of elasticity is 30 into 10 power 6 psi for steel, 15 into 10 power 6 psi for the brass, and 10 into 10 power 6 psi for the aluminum. So for all the three materials, we know the moduli of elasticity. Knowing that the beam is bent about a horizontal axis, by a couple of moment 12 kilopound inch. So moment is around horizontal axis, which is 12 kilopound inch. Determine in part A the maximum stress in each of the three materials. Maximum stress means stress at the outer surface of each of the three materials. So for steel, this is the outer surface, for brass, this one, for aluminum, this one. So we have to find their distances C for each of them after transforming it into the new area, and it will be the same actually. C will be the same, height will remain the same. And in part B, we have to find radius of curvature of the composite beam. Radius of curvature of the composite beam is rho. We have discussed it in our theory, and we will find rho here as well. First, we have to find N. Here are three materials. Before this, we were solving problem for two different materials. Now we have three. Among them, the smallest E is for aluminum, 10 into 10 power 6. So I will take it as a base material, and I will transform steel and brass into aluminum. So we will have two values of N for steel and N for brass. N for steel is E for steel divided by E for aluminum, and N for brass is E for brass divided by E for aluminum. So we will do it. Problem number 455, I think. Yes, 455. N for steel is E for steel divided by E for aluminum. E for steel is given to us. It is 13 to 10 power 6. E for aluminum is 10 into 10 power 6. So it comes out to be 3. N for brass is E for brass divided by E for aluminum. It is 15 into 10 power 6 divided by 10 into 10 power 6. So this comes out to be 1.5. We have two values of N. So we will multiply N for steel, NS with the width of the steel section, and NB with the width of the brass section. Okay. Just remember that the center strip is for steel, and the strips above the steel and below the steel are brass, and aluminum will remain the same. Here I want to explain a few things on this slide actually. Aluminum will remain the same because our basic material is aluminum. Width of brass 1.5 will be multiplied by N, it will increase, and width of steel will be multiplied with N for steel, and it will also increase. Initial width is 1.5 for all. So width for steel, transform width actually, BS transformed will be 1.5 into NS, and B brass transformed will be 1.5 into N for brass. 1.5 is its initial width, and transform width of aluminum will remain the same. Okay, this will be 1.5 into 3. 1.5 into 3 becomes 4.5 inches, and 1.5 into 1.5 will be 2.25 inches. So the new width of steel will be 4.5 inches, and the new width of the brass section will be 2.2 inches. Aluminum will remain the same. So I will draw it. Outermost section was aluminum. It will remain the same, 1.5. Next section was brass. It will increase. It is 2.2 now. And the third one is steel. It has further increased. It is 4.5. After steel again we have brass, it will be 2.2. After brass we have aluminum at the bottom, it is 1.5. So this width is 1.5 inches. This width is 2.2 inches and this width is 4.5 inches. Now this whole cross section is assumed to be made from aluminum because we have transformed steel and brass into aluminum. Steel has its own value of N and brass has its own value of N. That is why they have different widths. Okay. Height of each section is same. It was 0.5 inch each. Okay. The centroid is actually the geometric center and it is the midpoint between the top and the bottom layers because it is symmetric. Okay, now we have to find I. I for the aluminum section, I for the brass section and I for the steel section. So it is very easy. We also know D, we also know D for each of them. So total I will call it area 1, area 2 and area 3. I is equal to 2 times area 1, 2 times I of area 1 plus 2 times I of area 2 plus I3, because area 1 and area 2 and area 3, area 1 and area 2 are actually repeated twice at the top and at the bottom. So I will be 2 times I1. I1 is BH cube by 12. 1.5 H cube, 0.5 cube divided by 12 plus AD square. What is A? Area of section 1. It is 1.5 into 0.5. This is A. What is D? D is distance of the centroid of area 1 from the centroid of the total cross section. So it is actually 0.5 plus 0.25 plus 0.25. It is 1. D1 is 1. Plus 2 times I2. What is I2? For section 2, we have D2, distance of centroid of section 2 from the centroid of the total cross section. It is 0.5 plus 0.25 plus 0.25, so it becomes 0.5 inches. Section 2 has a width of 2.2, height is 0.5 divided by 12 plus area of section 2 is 2.2 into 0.5. D of section 2 is 0.5. Okay. Plus I3, section 3. Its width is 4.5. Its height is 0.5 divided by 12 plus AD square. D of section 3 is 0 because the total centroid of the cross section and centroid of section 3 are area 3. They are matching each other, they are coincident, and there is no distance between the total cross section centroid and centroid of the area 3. So D3 is 0. We do not need to add it here. So total I becomes, by adding 2 times I1 plus 2 times I2 plus 2 times plus I3. So it becomes 1.0234 inch power 4. Sorry, there is a mistake in calculation. I will be 2.1875 inch power 4. Okay, we have found I. Now we have to find maximum stress in aluminum, brass and steel separately. So maximum stress in aluminum is equal to MC for aluminum divided by I. So C for aluminum, M is actually given to us. It is 12 kilopound inches, 12 into 10 power 3. C for aluminum is distance of the outer surface of aluminum from the neutral axis. Distance of the outer surface of aluminum from the neutral axis. This is Ca, which becomes 0.5 plus 0.5 plus 0.25. So it is 1.25 inches. Similarly, if we want to find C for brass, distance of the outer surface of brass from the neutral axis, it will be Cb, and it is 0.5 plus 0.25, it becomes 0.75 inches. And distance of the outer surface of steel from the neutral axis, C steel, is 0.25 inches. We will use these values. Okay, so sigma for aluminum, maximum stress in aluminum is MCA over I. M is 12 into 10 power 3. Ca has been calculated, it is 1.25, and I is 2.1875. So it becomes 6.86 into 10 power 3 psi, or 6.86 ksi. Sigma for brass is N of brass into M C over I. This C is for brass. So N for brass has been calculated earlier. It is 1.5. M is 12 into 10 power 3. C for brass is 0.75. And I is 2.1875. So sigma brass becomes 6.17 into 10 power 3 psi, or 6.17 ksi. Okay. The next one is sigma, or maximum stress in steel. It is N of steel, M C of steel divided by I. Remember that we have multiplied N with the stress value of brass and N with the stress value of steel, but we have not multiplied N with the in the expression of stress for aluminum, because N for aluminum is 1. We have replaced all of the materials with aluminum, so there is no need to multiply N with the stress of aluminum, because N for aluminum will be 1. Okay, here N for steel is 3, M is 12 into 10 power 3. C for steel, it is 0.25 divided by I is 2.1875. So sigma for steel becomes 4.11 into 10 power 3 psi, or 4.11 ksi. So the first part of the problem was to find maximum stress in aluminum, brass and steel. We have found it. In the second part, part B, we were asked to find radius of curvature. Radius of curvature is 1 over rho. The formula is 1 over rho is equal to M over EI. M is given to us, I is known to us. There are 3 different materials. Which I we have to use? Because this I, which E we have to use actually. E is given for aluminum, steel and brass. Because we have transformed the whole cross section, or the composite cross section, into an aluminum material. This transform cross section is made of aluminum, so we will use E for aluminum because I has been calculated for this transformed cross section. By putting the values, 12 into 10 power 3 is moment, E for aluminum is 10 into 10 power 6, and I is 2.1875. So rho will become 1823 inches, or if you divide it by 12, it will be 151.9 feet. We were asked to find radius of curvature, so we have calculated rho. If we were asked to find curvature only, so it will be 1 over rho. It is 548.57 into 10 power minus 6 per inch. But radius of curvature was asked. So this is the solution of the problem. We just converted the cross section into aluminum. We have replaced steel and brass both with the aluminum. So we have two values of N, one for steel and the other for brass. In the previous problem, I have a doubt in the previous problem. There's a mistake, or I missed something in the previous problem. In problem number 4.39, we have N equal to 1.4. We have to multiply this value of N with in the expression of brass here, because we replaced N with we replaced brass with we replaced copper with aluminum in the previous problem. So we have to multiply N with N in the expression of copper. The net value is same. I did a mistake in writing N here. It is 1.4. You can do the calculations by yourself again. If there is any problem in the calculations, you can correct it again. Okay. Now I will move towards our next problem, which is problem 458 from the exercise. A steel pipe and an aluminum pipe are securely bonded together to form the composite beam shown. The modulus of elasticity is 200 gigapascal for steel and 70 gigapascal for aluminum. Knowing that the composite beam is bent by a couple of moment, 500 Newton meter, we have not been told that this moment is around a horizontal axis or a vertical axis, but whatever it is, since it is a circular cross section, it is axisymmetric. So either it bends about horizontal axis or vertical axis, the behavior will be same. Determine the maximum stress in the aluminum and in the steel. Maximum stress in aluminum and steel, both, it will be at their outer surfaces, outer layers. So at outer layers, we know the C, it is given to us, it is from the center to the outer surface, distance from center to the outer surface. And first we have to transform this into a single material. How to transform this into a single material? Modulus of elasticity of steel is greater than modulus of elasticity for aluminum. So we will find N by dividing ES with E aluminum. It is 200 divided by 70. So it will become 2.86. Okay, I will move towards its solution. For 58, N is equal to N for steel divided by N for aluminum. 200 divided by 70, it becomes 2.68. Okay. Now we have to find I. Since it is circle, so for circle I is equal to pi by 4 radius power 4. It is a hollow cross section, so outer radius power 4 minus inner radius power 4. Okay. Total I is equal to I for aluminum section plus I for steel section. We have replaced steel with the aluminum section. Okay. I for aluminum is pi by 4. Outer radius of aluminum power 4 minus inner radius of aluminum power 4. For aluminum, outer radius is 19 mm and inner radius is 16 mm. So pi by 4, 19 power 4 minus 16 power 4, it becomes 50882.139 millimeter power 4. I for steel, since we have replaced steel with aluminum, so we have to multiply I for steel with n, pi by 4, outer radius of steel section minus inner radius of steel section power 4. N is 2.86 into pi by 4. Outer radius of steel is, here it is 16 and inner radius is 10. 16 power 4 minus 10 power 4, and it will be 124,747.4 millimeter power 4. Now we will add the two, IA plus IS, and the total I will be 175,629.539 millimeter power 4. Or if we want to convert millimeters into meters, 1 millimeter is 10 power minus 3 meters. So it will be 10 power minus 12 meters power 4, or it is 175.629 into 10 power minus 9 meter power 4. I is known to us. C is distance of outer surface from the centroid. Centroid in this case is passing through the center because it is a symmetric body. So from center, distance of the outer surface of aluminum is its radius, which is 19 mm or 0.019 meters, and outer surface of steel has a distance equal to its radius, which is 16 mm or 0.016 meters. So maximum stress in part A, maximum stress in aluminum, C for aluminum is its outer radius, which is 0.019 meters. So sigma aluminum is M, C for aluminum divided by I. M is given to us 500 Newton meters. C for aluminum is 0.019 meters divided by I is 175.629 into 10 power minus 9 meter power 4. So sigma for aluminum becomes 54 into 10 power 6 pascals, or it is 54 megapascals. In part B, we have to find sigma for steel, but now we have to multiply it with N because we replaced steel with aluminum initially. So the value of stress must be multiplied with the value of N for steel. M, C for steel, or I. N in this problem is 2.86. M is 500 Newton meter. C for steel is its outer radius, which is 0.016 divided by I is 175.629 into 10 power minus 9. So this comes out to be 130.27 into 10 power 6 pascals, or we can rewrite it as 130.27 megapascals. 10 power 6 pascals are equal to megapascals, 1 megapascal. Okay, so it was very simple. We use the same formula MC over I, but we multiply the value of stress for steel with N because we replaced steel with aluminum. Before that we found I. In I, we multiply a value of I for steel with N because we replaced steel with aluminum, and N is simply a ratio of the greater modulus of elasticity over the smaller modulus of elasticity. Okay, we will move towards the next problem, which I have chosen for this lecture is problem 451. This is a reinforced concrete beam. Knowing that the bending moment in the reinforced concrete beam is 100 kilopounds feet, and that the modulus of elasticity is 3.625 into 10 power 6 psi for the concrete and 29 into 10 power 6 psi for the steel. Determine the stress in the steel and the maximum stress in concrete. In the theory part of this chapter, we discussed about reinforced concrete beams, and we have solved a numerical problem or a sample problem on it. The difference is that in this problem the concrete section is actually a T shape. So we have to divide this concrete section into the transformed section like this one. Here a neutral axis passes from the bottom of the concrete section, and then we have area of steel, n times area of steel, because we have to replace steel with the concrete. Steel has higher modulus of elasticity. Now we know that top flange of the T section is 4 inches. It is there. Then we assume that there is x. Total depth of the steel rods from the top, this is known to us. This is important for us. It is 20 minus 2.5. 20 minus 2.5 is 17.5 inches. So this total depth is 17.5 inches. So the remaining one from neutral axis to steel is 17.5 minus 4 minus x. 17.5 minus 4 becomes 13.5. So it is 13.5 minus x. Okay, I will draw this figure here. Before that, we will find n. 4.51. N is E for steel divided by E for concrete. E for steel is 29 into 10 power 6 psi, and E for concrete is 3.625 into 10 power 6 psi. So n comes out to be 8 in this case. Okay, now I will draw the transform section here. I have chosen this problem just because it is a little different from the sample problem which we solved during our theoretical lecture of theory part. It is a T section, so it is a little bit different than that. Steel has been transformed into concrete. Here is our neutral axis. From neutral axis, above the neutral axis, the flange of T section is 4 inch deep. The remaining height is unknown, it is x, and depth of the steel section from the top is 13.5 minus x. First we have to find this x. If we know x, we know the location of the neutral axis. Okay. Area of steel. Let us find area of steel. Area of steel is area of the single steel rod multiplied by number of rods. Single steel rod has a diameter of 1 inch. So we will find its area pi by 4 into 1 square. This is area of the single rod. Then we have a total of 4 rods here. It is given 1, 2, 3, 4. So we will use it. We will multiply it with 4. So area of steel becomes 3.1416 square inch. And N times area of steel, NAS, becomes 8 multiplied by 3.1416. It is 25.133 square inch. Okay, now we will find location of neutral axis. So for that we need to find x. As discussed earlier, around the neutral axis, summation of the first moment of area must be equal to 0. Summation of first moment of area above the neutral axis minus summation of moment of area below the neutral axis will be equal to 0. Above the neutral axis we have two areas, area 1 and area 2. Below the neutral axis we have only a single area, area 3. Area 1 is equal to 24 into 4, and its distance from the neutral axis, the distance of its centroid from the neutral axis is x plus 2. Distance of the centroid of this area from the neutral axis is x plus 2. Okay, plus there is another area, area 2. This area, this is actually 12. This area is 12x into distance of its centroid from the neutral axis is x by 2 minus area 3 is NAS into distance of its centroid from the neutral axis is 13.5 minus x is equal to 0. We have to simplify this expression. This expression after simplification becomes 6x square plus 121.133 x minus 147.3 is equal to 0. This is a quadratic expression. We have to find the value of x. After solution you will find two values of x. The positive one for us is actually the actual value. Negative value of x does not exist. So it is 1.15 inch. So this value of x here, it is 1.15. Okay, I should not write it here. Okay, x is known to us. Now we have to find I. Previously we derived an expression for I, but this beam is this cross section is a little bit different. It is not a simple rectangular cross section. It is a P section. So I will be I for section 1 plus I for section 2 plus I for section 3. Okay, I for section 1 is B1 H1 cube by 12 plus A1 D1 square. B1, okay, I'll write it here. B1 H1 cube over 12 plus A1 D1 square. So B1 is 24 inches, height is 4 inches. 24 into 4 cube divided by 12. Area is again 24 into 4. D1, distance of centroid of the section 1 from the neutral axis, it is x plus 2. X plus 2. So x is 1.15 plus 2. It becomes 3.15 square. So the sum becomes I1 becomes 1080.6 inch power 4. I2 is B2 H2 cube divided by 12 plus A2 D2 square. So B2, width of section 2 is 12 inches, Height of section 2 is x, which is 1.15 inches. So 12 into 1.15 cube divided by 12 plus area is 12 into 1.15, 12x, and d2 is actually distance of the centroid of section 2 from the neutral axis, which is x by 2. X by 2 means 1.15 divided by 2. divided by 2. So this becomes 6.1 inch power 4. I3 is B3H3 cube divided by 12 plus. Now I3 is actually, our area 3 is made of steel, but actually it has been transformed into concrete. So this area is actually now NAS into D3 cube, D3 square. B3H3 cube divided by 12. Height of this section, of this transformed steel section, is very small. This height is very small, this one. And if we take its cube, it will be really very small and we can neglect it. So usually we neglect this term of the steel section. So NAS into D cube. NAS is known to us. It is 25.133, and D3 is depth of or distance of the centroid of the steel section, steel area, transformed steel area from the neutral axis, which is 13.5 minus x, 13.5 minus 1.15. NAS is equal to 25.133 into 13.5 minus 1.15, it becomes 12.35. So this comes out to be, I3 comes out to be 3.3 inch power 4. So now we can find I, which is sum of I1 plus I2 plus I3. We can add these values and I becomes 4920 inch power 4. Now we have to find maximum stress in steel and maximum stress in concrete. First we will find maximum stress in concrete, part B. First part B, concrete. So it is M C for concrete divided by I. M is given to us in this problem. It is 100 kilopound feet. Kilopound feet. Let me first convert M into pound inches. Kilopound feet. Okay, 1 kilopound is equal to 10 power 3 pounds and 1 feet is equal to 10 power 6 feet. So 100 into 10 power 3 pounds. 1 feet is equal to 12 inches. 1 feet is equal to 12 inches. So I will multiply it with 12. It becomes 1200 into 10 power 3 pound inch. So 100, the value of M will be 1200 into 10 power 3. C for concrete is distance of the outer surface of concrete from the neutral axis. Distance of the outer surface of concrete from the neutral axis is here. It is x plus 4. X is 1.15 plus 4. So it is 5.15. C for concrete is x plus 4. It is 5.15. (5.15) divided by I is known to us, 4920. So sigma for concrete, maximum stress in concrete becomes, and it will be negative actually. Concrete is always under compression, so we will keep a negative sign intentionally. Sigma for concrete becomes minus 1.256 into 10 power 3 psi. So I will write it as KSI. 10 power 3 psi becomes 1 KSI. In part A, we were asked to find sigma for steel. So sigma for steel, because we transformed steel into concrete, so we have to multiply sigma for steel with N into MC for steel divided by I. N was 8, we calculated it. M is 1200 into 10 power 3. C for steel is distance of the outer surface of steel from the neutral axis, which is here 13.5 minus x. 13.5 minus x, 13.5 minus 1.15, it becomes 12.35. 12.35 divided by I, which is 4920. So sigma for steel becomes 24.1 into 10 power 3 psi, or 24.1 ksi. This is simple. We calculated N by dividing greater E over smaller e. E for steel is greater than E for concrete. So N is 8. We transform area of steel into concrete. It is NAS, N times area of steel. Above the neutral axis is concrete, below the neutral axis is steel, because concrete cannot withstand tension and steel is made to bear tension actually. Concrete is made to bear compression. So we kept compression material above the neutral axis and tensile material for tension under the neutral axis. First we used summation of first moment of area around neutral axis equal to 0. So we found the value of x. Then we found moment of inertia for the three parts, part 1, 2 and 3, and we have added them to find total moment of inertia I. Then we used this expression MC over I to find maximum stress in concrete, and N times MC over I to find maximum stress in steel. And if we plot it here, the T section, this is the T section. Above the neutral axis there is compression. I will plot its side view. Above the neutral axis is compression, where sigma C is equal to minus 1.256 KSI. At neutral axis it is 0, stress is 0, and below neutral axis there are steel bars. So at steel bar there is tension, sigma S equal to 24.1 KSI. I hope you have understood all the solutions of the selected problems. If there is any problem or if there is any query you want to discuss, you can send me an email and I will try to respond. Thank you very much.